It is generally necessary to pull an equipment grounding conductor, or EIC, to a subpanel of a separate building. The EGC serves as a safety measure to protect against electrical shock and ensure proper grounding of the electrical system. According to the National Electrical Code, NEC, Article 250.24, A5, an EGC is required for service panels, distribution panels, and subpanels that are located in a separate building or structure. The EGC must be run with the other circuit conductors and must be sized according to the requirements of NEC Table 250.122. The EGC provides a path for fault currents to flow back to the grounding electrode system of the main service panel. In the event of a fault, such as a short circuit or ground fault, the EGC will carry the fault current back to the source, preventing dangerous voltages from accumulating on the electrical system. Additionally, the EGC helps to equalize the potential between the two buildings, reducing the risk of electrical shock and ensuring the safe operation of the electrical system. Therefore, it is essential to install an EGC to a subpanel in a separate building to ensure the safety and proper functioning of the electrical system. The purpose of the equipment grounding conductor, or EIC, is to provide a low impedance path for fault current to return to the source. This path allows overcurrent protected devices, such as circuit breakers or fuses, to quickly and safely clear the fault, minimizing the risk of electrical shock or fire. Without an effective EGC, fault current may flow through unintended paths such as metal enclosures, water pipes, or even the earth, creating a dangerous shock hazard. Firstly, the EGC connects the metal enclosures of electrical equipment to the grounding electrode system. This ensures that all metal parts are at or near ground potential, preventing voltage differences that could cause electric shock. Secondly, in the event of a ground fault, the EGC provides a low impedance path for fault current to flow back to the source. This high current flow causes the overcurrent protective device to trip, quickly disconnecting the circuit and preventing further damage or injury. Thirdly, the EGC helps to equalize the potential between different parts of the electrical system. This reduces the risk of stray voltages or circulating currents that could interfere with the operation of sensitive electronic equipment. The size of the EGC is determined by the size of the circuit conductors, as specified in NEC Table 250.122. It is important to use the correct size EGC to ensure that it can safely carry the maximum available fault current. The EGC must be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the ground fault path is minimized. The EGC must be connected to the grounding electrode system at the service equipment. This provides a direct connection to earth, ensuring that the entire electrical system is properly grounded. In a separate building, the grounding electrode system must be supplemented by an additional grounding electrode, such as a ground rod or ground ring. This ensures that the building has its own independent grounding system, which is especially important in case of a fault on the primary service. When running an EGC to a separate building, it is important to maintain the integrity of the ground fault path. This means avoiding any unnecessary splices or connections and using proper grounding techniques. The EGC should be continuous and unbroken from the subpanel back to the main service panel. This ensures that the ground fault path remains low impedance and effective. In some cases, it may be necessary to use a larger EGC than required by NEC Table 250.122. This may be necessary if the impedance of the ground fault path is high or if the available fault current is very high. The local authority having jurisdiction, or ODG, should be consulted to determine the appropriate size EGC for the specific application. It is important to remember that the EGC is a critical safety component of the electrical system. Proper installation and maintenance of the EGC are essential to ensure the safety of people and property. If there are any questions or concerns about the EGC, a qualified electrician should be consulted. The NEC provides detailed requirements for grounding and bonding of electrical systems. These requirements are designed to ensure that the electrical system is safe and reliable. It is important to be familiar with the NEC requirements for EGC and to follow them carefully. The EGC is not intended to carry normal operating current. It is only intended to carry fault current in the event of a ground fault. If the EGC is carrying normal operating current, there is a problem with the electrical system that needs to be corrected. The EGC should be inspected regularly to ensure that it is in good condition. Any damaged or corroded EGC should be replaced immediately. The EGC is an essential part of a safe and reliable electrical system. Proper installation and maintenance of the EGC are critical to protect against electrical shock and fire. Always consult with a qualified electrician if there are any questions or concerns about the EGC. Here are some additional points to consider about equipment grounding conductors EGC in separate buildings. The NEC addresses specific requirements to ensure safety and proper functioning of electrical systems in such scenarios. Firstly, the purpose of an EGC is to provide a low impedance path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault quickly. Secondly, in a separate building, this becomes even more critical because the building might have its own independent electrical system, but it's still connected to the main service. The EGC helps maintain a common ground potential between the two buildings, reducing the risk of voltage differences and potential shock hazards. Thirdly, NEC Article 250 covers grounding and bonding requirements. Specifically, 250.32 addresses grounding requirements for separate buildings or structures. This section mandates that an EGC be run with the circuit conductors to the separate building. This EGC must be sized according to Table 250.122, which correlates the EGC size with the size of the ungrounded conductors. The EGC should terminate at the grounding electrode system of the separate building. The grounding electrode system typically consists of items like ground rods, ground rings, or metal underground water pipes. The connection to the grounding electrode system should be made using appropriate connectors and methods as outlined in the NEC. An important exception to note is when the separate building is supplied by a single branch circuit and meets specific conditions outlined in the NEC. In such cases, the grounding requirements may be different. However, this is a very specific scenario and should be carefully evaluated by a qualified electrician. Running a separate EGC helps to minimize voltage drop and impedance in the ground fault path. This is essential for ensuring that overcurrent devices operate quickly and effectively in the event of a fault. A low impedance ground fault path also helps to reduce the risk of stray voltages or circulating currents that can interfere with sensitive electronic equipment. Proper installation of the EGC includes ensuring that it is securely connected to all metal enclosures and equipment within the separate building. This helps to ensure that all metal parts are at or near ground potential, minimizing the risk of electric shock. Regular inspections of the grounding system in the separate building are important to ensure that it remains effective. Look for signs of corrosion, damage, or loose connections. Any issue should be addressed promptly by a qualified electrician. When working on electrical systems in separate buildings, it's essential to follow all applicable safety procedures and guidelines. This includes wearing appropriate personal protective equipment, or PPE, such as gloves and safety glasses. It also includes using properly insulated tools and equipment. The NEC is a comprehensive document that provides detailed requirements for electrical installations. It is important to stay up to date with the latest edition of the NEC and to be familiar with the specific requirements that apply to your work. State and local electrical codes may also have additional requirements that must be followed. These codes may be more stringent than the NEC in some areas. Consulting with a qualified electrical inspector can help ensure that your work meets all applicable code requirements. An EGC provides a safety net that can protect people and property from electrical hazards. By providing a low impedance path for fault current, the EGC helps to ensure that overcurrent devices operate quickly and safely, minimizing the risk of electric shock, fire, or equipment damage. In addition to the EGC, other grounding and bonding measures may be necessary to ensure the safety and proper functioning of the electrical system in a separate building. These measures may include bonding metal water pipes, gas pipes, and other metallic objects to the grounding electrode system. Bonding helps to equalize the potential between different metal parts, reducing the risk of electric shock. Surge protection devices, or SPDs, can also be installed to protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. SPD should be installed at the service entrance and at any subpanels within the separate building. Proper grounding and bonding are essential for creating a safe and reliable electrical system in a separate building. By following the requirements of the NEC and consulting with a qualified electrician, ensure that the electrical system is properly grounded and bonded. Firstly, the EGC carries fault current back to the source, tripping the breaker. Secondly, it maintains a common ground potential between buildings. Thirdly, NEC Article 250 covers this requirement. Fourthly, the EGC size is based on Table 250.122. Fifthly, the EGC must connect to the building's grounding electrode system, for example, ground rods. Sixthly, carefully consider any exceptions. Seventhly, running a separate EGC minimizes impedance. Eighthly, ensure secure connections to metal enclosures. Ninthly, inspect the grounding system regularly. Tenthly, always follow safety procedures and wear PPE. The NEC requires a grounding electrode system in a separate building connected to the EGC. This system can include ground rods, ground rings, or metal water pipes, supplementing the grounding provided by the EGC run from the main building. The grounding electrode system provides a local ground reference, enhancing safety and fault current path. When a fault occurs, the current flows through the EGC back to the source, tripping the overcurrent device, and also to the local grounding electrode system, providing an alternative path and minimizing voltage rise. Without the EGC, the reliance on the earth as the primary fault current path would be insufficient. The earth's impedance is too high to facilitate quick tripping of overcurrent devices. This could lead to prolonged exposure to fault voltages, creating a significant shock hazard. Furthermore, without the EGC, voltage potential differences could develop between the two buildings. This difference in potential could create a shock hazard if someone were to come into contact with grounded metal parts in both buildings simultaneously. The EGC ensures that both buildings are at approximately the same ground potential, minimizing this risk. The NEC specifies that the EGC must be sized according to the ungrounded conductors. This ensures that the EGC has sufficient ampacity to safely carry the maximum available fault current. The EGC must be installed in the same raceway or cable as the circuit conductors. This minimizes impedance and ensures a fast, effective fault current path. The connections to the EGC must be made with listed connectors, ensuring a reliable and low impedance connection. The EGC must be continuous and unbroken from the subpanel in the separate building back to the main service panel in the primary building. Splices are generally not permitted in the EGC, as they can increase impedance and reduce the effectiveness of the ground fault path. In some cases, an isolated ground conductor or EG may be used in addition to the EGC. The IGC provides a separate, dedicated ground path for sensitive electronic equipment, minimizing noise and interference. However, the IGC is not a substitute for the EGC, which is still required for safety purposes. The installation of an EGC to a separate building is not just a code requirement, it is a fundamental safety practice. It protects people and property from electrical hazards and ensures the reliable operation of electrical equipment. The EGC works in conjunction with other safety measures, such as overcurrent protection and ground fault circuit interrupters, or GFCIs, to provide a comprehensive safety system. These safety measures work together to minimize the risk of electric shock, fire, and equipment damage. Regular inspections and maintenance of the grounding system are essential to ensure that it remains effective. Look for signs of corrosion, damage, or loose connections. Any issues should be addressed promptly by a qualified electrician. If there are any questions or concerns about the grounding system, consult with a qualified electrician. An EGC is an important component of a safe electrical system in a separate building. Proper installation and maintenance of the EGC are essential to protect people and property from electrical hazards.